Hello everyone, let's get started. Today I am going to present one of my research findings with the title of Numerical Simulation of the Bond Behavior between Concrete and GFRP Reinforcing Bars. So these are the contents of today's presentations. After the introductions, so I will discuss experimental approach. Then we will focus on some available bond models in the literature, then a finite element modeling, finally parametric study and conclusions. Let me start with the brief introduction of concrete element. Concrete is the material which is weak in tensions. So therefore we provide steel bar to enhance its tensile capacity. Because of the inside the concrete members, it is favorable for the corrosions. The steel bar getting corroded when during its lifespan. So therefore people used some supplementary material for the steel bars. So one of the option is the using fiber reinforced polymer bars. There are three types of polymer bars available: glass fiber, carbon fiber, and amide fiber. Out of these three, GFRP is the cost-effective option. GFRP bars have a lot of advantage when compared with the steel bars. Especially it do not corrode, it has very low weight strength ratio, it has very high strength as well. There are other properties listed in these slides. In these tables you can see some important properties of fiber reinforced polymer bars. So it's very importantly, it has very high tensile strength compared with steel. Civil engineers encounters one of the major issue while they are using FRP bars is the bond behavior of the bars. So this bond behaviors, it depends on the many factors such as manufacturing process, mechanical properties, and environmental condition which is inside the concrete. So if you want to study in-depth analysis of the bond performance, we should know how this bond stress transform between the concrete and bars. So it's purely depends on the chemical bond and friction of the bar surface and the irregularity of bar surface such as ribbed, sand coated bars or plain bars. The bond performance affected by the many factors listed in these slides, especially the concrete strength, bar diameters, and embedded length are the most severe affecting factors. So therefore, studying of bond performance is very complex behavior. Therefore, we have to select suitable approach. So one of the best approach is the experimental ones. There are two type of tests commonly used to analyze the bond performance. One is the direct flow test, another one is the beam type flow test. So ultimate goal of the researchers, finally, they propose many bond slip models to explain the entire behavior of bond performance. So these are the some of the popular models available in the literature: BPE, modified BPE, Malvars, and CMR models. Apart from the previous models, some international standards, they focus mainly on the bond strength rather than considering the entire bond behaviors. So here I have listed some of the most popular design codes available in the industry. So as you can see here, they have provided the equation for the bond strength. So this equation for ACI code, this is for the Canadian standards. So here what I have done, I compared all these four standards against the variables for the study. As you can see here, embedded length especially considered only in ACI codes, but even though all the codes, they have not included in their models. So also you can see none of the codes considered all the factors affecting the bond performance of the bars. So therefore, this area is still open for the future researchers. So what I have done in this study, I have models finite element modeling using the Abacus software. So for this, I have taken the experimental findings from these gentlemen. So because of the axisymmetry nature of the problems, I have modeled only 1/4 of the total problems. So for this case, I used concrete damage plasticity model to define the properties of concrete, and I use the Hessian model to define the properties of GFRP bars. So after the finite element analysis, I have done the mesh sensitivity analysis. So after selecting the proper mesh size, so for the output, I have measured load and the slip in two different ends as similar to the experimental setup. So from the finite element analysis, I compared the results with the experimental finding. You can see this is the compression damage, then this is the tension damage. So it's also, you can see it's perfectly replicate the experimental one. Then finally, the entire behavior of bond performance is compared with the experimental one. So as you can see, these finite element results is most close to the experimental findings. Once the model is calibrated, I have conducted the parametric study. For this, I have selected the variable as listed in these tables. So you can see the compressive strength I have selected as 20 to 60 megapascal. Then bar size I have selected as 10, 13, and 16. Embedded length, it varies from 2 to 5 times diameter of the bar. So this slide shows the results of the parametric study. As you can see here, when the concrete strength is increased, the bond strength also increase, but when the diameter and embedded length is increased, the bond strength is reduced. So at the end, what I have done, I developed a suitable bond slip models to explain the entire behavior of the bond performance. So what I found, we can able to simplify it as bilinear models. The necessary equations are listed here. The K factors should be calculated based on the bar types. So for example, here I have included for one type of bar, polyester resin GFRP bars. For this necessary K factor I have obtained from the finite element study. So what I have done this one, I compared this proposed model with the finite element findings. As you can see here, for different specification of bars and concrete strengths, this proposed bond models is perfectly matched with the finite element ones. So apart from that, so I did one more additional things to verify my finite element techniques. I have taken another experimental results from these gentlemen. This time it's a beam pullout test results. So this one I compared with the direct pullout finite element test. As you can see here, finite element also follows the same trends like experimental one. Finally, uh, the experimental results, the maximum strength I compared with the available international standards and my proposed models. As you can see here, the value calculated using my models is more close to the experimental compared to the available standards. So at the end, the conclusions, I could able to model accurate enough numerical finite element models using the Abacus software with a tolerance of 3.5% in case of bone strength, 10% in case of bone slip. Also, as concluded in the previous researches, in finite element also I found the bone strength is increased while increasing the compressive strength, whereas bone strength is reduced when we select the large number of large size of the GFRP bars. Also, the bone strength is increased while reducing the embedded length of GFRP bars. Especially, as concluded in the previous studies, the direct pullout test gives slightly higher values compared with the beam type pullout test. This also concluded by many researchers previously. I also got the same thing from the finite element models. Finally, the bone slip behavior could be modeled as bilinear approximations, as I mentioned in my previous models. So thanks a lot.